it very little, and it'll have about 2% damping. But if you shake it so that it approaches its yield moment or more, it'll go up to 10% damping. So 10% damping is not such a bad approximation for our buildings. Then, if we take, forgive me for using jargon, but if we take a broadband earthquake, you know, one that has high velocity from about 0.5 seconds in the response spectrum to about 2 or even 3 seconds, then what happened was exactly this. And I don't want to take, do you want to take a break? There are too many of you started sleeping. It disturbs me. All right, I won't take a break. If you start with a system with 2% damping and you shake it, it softens, and when it softens, its response becomes low, and it also increases in damping, so it goes from the upper line to the lower line, and lo and behold, as something goes from, say, a 1-second period to a 2-second period, and goes from 2% damping to 10% damping, there is a reduction of 4 in the force. And that's all I was trying to do, show that Newmark was right. And he was right in this case, but don't take me too seriously. But what I didn't look at, and I should have, was this. If you think of the same picture in terms of displacement response in a single degree of freedom system and plotted versus period, as the system goes from 1 period to 2, 1 second to 2 seconds, the damping increases, so the displacement remains about the same. Hey, do you see, I'm in a way denying science. I'm saying that the drift doesn't increase with respect to the linear model. But that's what it was. I didn't accept it, because it didn't seem to satisfy. Now, at the same time, and this is important, another student, Dr. Algan, working on the meaning of drift on the banking, on money, so to speak, looked at how much of the cost could, say, walls maintain for a given drift. And he found that, in general, by the time you went to a drift ratio, you know what I mean by a drift ratio, right? The distortion of the system. By the time you went to a drift ratio of 1%, you had really lost all of the value of the attachments, if they were attached to the walls. So this worrying about whether steel or reinforced concrete will take 2% drift is a waste of time. You don't want to go that way if you want to protect the bankers. He also asked about 300 engineers by mail in Mexico, in Japan, in United States, and Canada as to what they thought would be a limiting drift. Now, of course, that depends on how the person who's answering the question calculates drift. But about 40% of the engineers thought 0.5% was all they could retain. About 80% thought 1%. And by the time you went to 2%, everybody was on board that you shouldn't do more than that. And you know what? Brittle structures can even make 2% drift. So suddenly, the maximum drift didn't become a problem. But another confession. Dr. Otani went to multi-story systems. And by using the Takeda hysteresis, he was able to simulate the measured response of a 3-story frame going into nonlinear response and actually calculated exactly. But of course, if something is measured, you can always calculate it exactly. But still, he was able to do it, and his method is still used in very many places. But more importantly, when he plotted his measured maximum drift versus spectrum intensity, Hausner's spectrum intensity, which was another way of saying velocity, he found out that there was a linear increase. God, it was too easy. I didn't see it. I mean, I plotted it myself. I was there, but it didn't occur to me how easy it was, because I was still thinking of complicated hysteresis loops. And then we tested a whole bunch of frames with walls, etc., until Dr. Shimazaki, starting with a very complicated method. Hey, don't give up hope. I'm going to come to a very simple conclusion. Decided that over what he called, on the basis of his energy approach, the period Tg, he could calculate the nonlinear response using a linear model, but using 2% damping. But he had trouble on this side. And indeed, we struggled with that for a couple of years until Andres Lepaje, somebody from Maracaibo, showed that you could do the whole thing like Otani had done, linearly, ignoring everything else. And it was just too simple for words to be able to calculate with reasonable correctness, plus or minus 20% is damn good in this business, that he did it. I won't even go into the other part, but look, are you all awake? Wake up. If you want to compute the nonlinear response of a frame or of a wall, you calculate the spectral displacement by taking the initial calculated period of the system and multiplying it by square root of 2 and multiplying it by 10 to get it in inches. Or, if you want to get it in millimeters, approximately the same thing. You don't have to do a nonlinear analysis. And this is good if your PGA is from 0.4 to 0.6, and if your PGV is below 400 millimeters. Actually, there is a closer correlation between drift and the ground velocity. You should be sensitive to it. And it would even work in Mexico City. But hey, folks, it's that simple. If you're awake, if she's not bothering you with questions, let me give you a very simple example. If the whole idea is to estimate, not calculate exactly, but to estimate the drift, and say you have a period of a building with 10 frames, 10 floors, and with a period of 1 second. Your displacement, spectral displacement, is 350 millimeters. It's that simple. And oh, I did that. And your roof displacement is approximately 25% more if your stiffness is reasonably uniform. That's all. You can estimate this in 2 minutes. But estimate, you're not calculating it exactly. Okay, that's what I want to say about earthquake engineering. Do I have time to talk about? There are too many people sleeping. Well, although maybe that's good. I'm making it possible for them to have a rest. Look, let me take a few moments to describe what I learned by studying the attacks, those ugly attacks on World Trade Center and on the Pentagon. May I have the next set of slides, please? But that's detail. Huh? This building didn't fail because it wasn't analyzed properly. It failed because of detail. Can we go to final two? No, we did that. I'm going to skip the videos. I'm sorry. Or maybe he's not. well, let me play this to a certain level just to point out something. You see, when the plane hit, it'll come again. When the plane hit on one side, it came out the other side. That's very important. And it took me time to realize that. This is not a real thing. This is Mickey Mouse. This is an animation. You understand that. But what I'm trying to point out to you is that the plane came in one end and went out the other end. And hey, let me take your time to show you this. Let's continue playing. We spent a lot of time on this thing. We spent 2 years to model the airplane, exactly. And you know what? When I called Boeing to ask for the drawings of the airplane, Boeing turned me into the Federal Bureau of Investigation. And then I was able to get the plans from a toy manufacturer in Moscow. But we had a perfect model, true to form, linear, of course, of the building and of the attack. But I want to show you what we really learned that was very important. And again, it has to do with if you're going to be wrong anyway, you should be wrong the easy way. And just think, there are people involved in here. See, that's what hurts, to remember this. The part that I want to show you will be coming up momentarily. You see, we knew what happened on the outside. We knew what broke coming in, and we knew what broke going out. But we didn't know what was inside. And all our analyses was to figure out what was inside. This is the modeling of the jet fuel, which is really what cuts. It's the mass that does the damage. Now, do I believe this? Well, it's approximately that's what happened. Huh? I was hoping I could accelerate this, but hey, Juan, maybe you can accelerate it. Yes, yes. See. Well, anyway, we look at it bit by bit, and finally we put everything together to get what we obtained out of it. Okay, let's cut it. Huh? And I have one of the Pentagon, but we don't have to look at this one. I won't take too much of your time, but there are a couple of interesting things. At the time, I was just finishing as chairman of a committee of the National Academy of Sciences and the Defense Department in essentially anti-terrorism. And we suddenly discovered that the recommendations we had were now related to the safety of almost everyone. It wasn't a special case. Now, how do you solve this vicious problem of terrorist attack? Well, the root of the problem is to first not to have the guys develop, not to get to hatred, not to develop to hatred, and then if there is going to be hatred, to keep them away. The last thing, the first thing is offset, keep them away, and the second thing is to improve the resistance of a building. But Jesus, we can't improve the resistance of every building in the United States. It's not so easy. And there were two extreme views within engineering, and then plus a radical one. Let me give you the Spanish part. The view of the neocomps was that this should be done only by special people who will do exact analyses. And of course, these was the group that wanted to make money out of the event. Because if you wanted to do exact analyses, then you had to go to them. They would make the money. What I call conservative, or if you wish, the liberal view, was that you tried to do the details and save the system like that. And the conspiratory belief was that the United States government did it. It wasn't done outside. It was a very sad thing sometime, but it's silly that they would do it. Now, the conspiracy theory said, how could the cut in front of the Pentagon building be smaller than the wingspan of the airplane? And indeed, the wingspan of the airplane was about 40 meters. The cut was about 30 meters. The other one was, they said, how can aluminum cut steel? How can an aluminum airplane hit a steel building and cut it? How can that happen? Hey, they're still asked that question. Oh. Look. Do you know how the Pentagon was built in the 40s? They saw that a war was coming up and they needed a building. But they thought, what were they going to do with this building after the war? It wasn't going to be used for anything, so they built it as a warehouse. Instead of designing it for, say, 300 kilograms per meter square, they designed it for 10 times that, which was good. They also designed the first floor with spiral columns, which was even better because of the toughness of these columns. And they anchored things elegantly. They built this with a code that was only about 50 pages long, small code, but they built a beautiful structure, and the Pentagon did not fail. It didn't kill anybody because of the failure that occurred afterwards. Now, the question, and trying to answer why. Why did it have a smaller gash in front than the wingspan of the earthquake? Well, look, what cuts is not the aluminum. What cuts is the fuel, the mass of the fuel in the wings. And as you go away from it, there is less and less mass. You see, you come with a mass at a velocity, then you reduce the velocity to a minimum. That means you have an acceleration or deceleration, and the mass times acceleration creates the force. And that is indeed a force in that case. And so as this thing moves, and that's exactly what happened. The columns cut into the fuselage. And to talk about something ghoulish, when you looked at the bodies on the floor, the bodies of the people who stole the airplane was right here. And then the passengers went further on and on. And what happened is that at the edges, the columns cut the wings, whereas near the fuselage, the wings cut the columns, and that's why it was smaller. It was that simple. You know, one didn't have to think very much about what happened. To me, this column is a hero because it absorbed a tremendous amount of energy to hold this thing back. And look at this. Do you see the ends of the bars? You must have been in a laboratory at one time in your life. You see those breaks? It didn't slip out, it fractured. And to fracture it, it took a lot of energy. And I think I admire the engineers who built the structure. The Pentagon building was a case of intrinsic strength and fire resistance, quite unintended. Really, they were not thinking of an airplane hitting the structure at all, but it worked out beautifully. Nobody was killed because of a structural failure. Of course, people were killed because the airplane hit something where people were working inside, but otherwise, no. Now, this is the other interesting thing. With the World Trade Center, what I was curious about is what had happened inside, because nobody who was inside came out. I mean, nobody who was inside at the level that the airplane hit came out. So our whole focus was on trying to figure out how many columns failed inside. And you must have, but some of you may have seen these scenes. It really breaks your heart when people jumped out of the building. What had they done? Well, anyway, that's something else. But like the true engineer that I am, I took the building model, I calculated its loads. With friends in the computer science department, we built a model that replaced it perfectly. And we found the drawings of the building in the Congressional Library, because initially the Defense Department wouldn't give it to us, but the Congressional Library did. And we built a very good model of the structure. We knew that, and we also had the navigation system, so we knew the speed at which it was going, and etc. But before that, we took a couple of fighter planes and modeled them exactly, and modeled the inside of the World Trade Center exactly, and let them fly through at the right speed. And we determined how many columns were lost because of it. Then, now that model took us about 6 months to build. This model took us 1 afternoon. It was essentially a barrel of water with wings full of water. And when we flew this model through the structure, we had the same result. So we had wasted our 6 months. But how could we have proven this any other way? You know, we had to have an exact model. But our focus was in trying to find out what was broken inside the building by calculation. And that also had a very funny result. We modeled the building exactly, we modeled the airplane exactly, everything exact. And we let it fly through. Pushing the wrong one. And of course, we did this, it took us 5 years to do all this. We went through and counted how many columns were destroyed because of it. And just to give you an interesting result, NIST made the same study. They said 9 columns broke. MIT, 12. WAI, 13. Purdue, 17. Kojima, the Japanese were interested. You know why? Because Japanese steel had been used in the building, and they were sensitive. But the guesses range from 21 to 9, And on this basis, I cannot tell you who is right, who is
Using
wrong.
data derived from the September
Now, let's look at it in simple terms. If you take steel and heat it, you lose 80% of its stiffness by the time it goes to approximately 700 degrees Celsius. The yield stress, by the time you go to 700 degrees Celsius, again, you lose about 80% of the yield strength of the system. And I can give you more complicated cases, but never mind, as long as I tell you that if you heat it to 70%, you lose 80% of the stiffness and 80% of the strength. And the strength, relative strengths of the columns were as shown here. And now you know what? After all these calculations, and I don't want you to mention it elsewhere because it ruins our years of work. If you looked at this, if you noticed that the weight of the mass of the fuel was in here, and you just wiped out those columns, that's as close a guess as you would from 5 years of calculation. It's that simple. I hope you will not have to do it, but if the occasion arises, think of it in those terms. Here again. In other words, we could have summarized our 5-year, I'm not exaggerating, 5 years of work in one afternoon by simply looking at this and saying the red columns will go. And we will be off by 30%, but so what? Because we found out that even if we lost no columns, I'm sorry if I lost your attention, this is probably the most important thing. Even if we had lost no columns, the building would fail. Now, the counter argument for that was that, hey, there was a big fire in Bogota, there was a big fire in Caracas, nothing happened. How do you explain that? It's very simple, because the airplane came in from one side and out the other. It scraped the insulation. The steel was exposed. And if you expose steel and take it up to 600-700 degrees Celsius, it's goodbye. It was that simple. Now, people will still not accept this. So even in this case, you could find a very simple solution by thinking and also looking. Thank you very much. Gracias.
Daremos inicio a la sesión de preguntas y respuestas. What if I want to go further the limits of the building code, trying to modify it or replace it with a new paradigm?
If you want to change it, if you want to change the building code,
I guess.
yes, it's very simple. All you got to do is find friends in big corporations who have money, and they will do it. They do it all the time. It's that simple. It's a matter of money, just like politics.
Do you think that the building codes like the ACE
ASCE, yes, or
or the ASD manual limits the human creativity?
Of course. Of course, because, look, now this is entirely my opinion, although I have worked with building codes for many years. There are 3 types of people who spend time. There are academics who want their name mentioned in the code. There are engineers who try to keep it simple. And there are salesmen who want to push their product in. And sometimes they make mistakes. But the most common mistake is that we convert the code into a cheap textbook. The code should never tell you how to design. The code should tell you what the limits are to the design. And in doing that, clearly, they don't always know the right limit and limit creativity. But hey, you can always take the risk and go outside the code, but if anything happens, your derriere is on fire.
Thank you. Is it okay for students in undergraduate level to use the code as a law, since the professors teach to use the code instead of teaching how to solve real-life problems?
Hey, unfortunately, our educational system confuses the code with physics. The code is not physics. In fact, it is against physics, as it is applied. And I should make another sales call. A book that we wrote about reinforced concrete with Professor Pujol, Professor Echinoza, and me is going to be put in sale this summer. And it has nothing to do with the code. It has to do with physics and observation. So I think that even in undergraduate classes, the code should not be taught. Physics should be taught. And experience should be taught, but not the code. The code should not be confused with physics, I think.
Okay, thank you.
We never have.
Can you explain us how did the World Trade Center in New York fail?
How did the World Trade Center? Oh,
It fell.
it was very simple. It got hot. It got hot and it was not insulated. You understand that, don't you? See, in Bogota, the building didn't fail. It burned for hours. In Philadelphia, the same thing. In Caracas, the same thing. But they had the insulation in place. In the World Trade Center, the insulation was scratched out. So if you expose steel to heat to as high as 600-700 degrees Celsius,
Thank you very much.
that's all. Thank you. Thank you very much. Thank you.
Ahora, el doctor Roberto Stark hará entrega de un pequeño reconocimiento al doctor Sozen por tan magnífica ponencia.
Oh dear, I forgot about that. Shall we drink it right now? Are they going to take a picture? You're going to get one too? Yes, you're going to get one.
Get one. Wow. So we can get drunk today.
Yes.